Okay, here we go. Business 720. Business 720. This is lecture 4b. And we're going to do, we did up through perpetuities. And what we're going to do now, this will be point 3 in the notes on section 4. So let's talk about annuities. So what's going on with an annuity, right? This is an equal sum of money received at regular intervals, right? So an annuity is a perpetuity that has a finite life, right? So we can take our lessons a little bit out of the previous case of the perpetuity. So this means that an annuity has, right, a maturity. That's what it's called. Right, perpetuities have no maturity. Now a regular annuity gives payments at the end of each time period, okay? So at the end of each time period. So to distinguish, there's also the non-regular annuity. This is called an annuity due. And there the payments are received there at the beginning, at the start of each time period. Okay. And let's do regular annuities. Okay, we'll do regular annuities. From the above, what you can say is that you know a present value of an annuity that would have never ended, right? If there was an actual perpetuity, right, that we know from above. So from 2, when we looked at perpetuity, right? So we know that it's the cash flow divided by the discount rate. Now let's suppose let's say that this is an equal payment. Let's say it's received through a last payment at the end of time period t equals 5. So right at t equals 5. The last payment in the annuity happens. Okay, so let's pretend that you're actually at time period t5, t equal 5, and you just received your last payment of C, right? So C is your payment. What would be the present value at time period t equal to 5, right, of remaining payments if the annuity continued without ever ending, if it was a perpetuity, right? So the present value in the 5th time period, right, would be C over R. It's like you're receiving C from the end of year 6 to infinity. Now, what is the present value at time period t equals 0 of a perpetuity that goes from year 6 to year infinity? So right, from year 6 to year infinity, we want to know what's the present value, right, at time period equal to 0. So, yeah, one way to think of this is to say, well, we could take the discounting method, just use the present value formula, right, for 5 years. Some people might think this, right? So we might say, well, the present value in year 0 is equal to C over R, right? And let's do a discount on that, which is 1 over 1 plus R. And we're going out to the 5th year, right? So that's the present value of the part of a perpetuity that you would not receive, right? So this is the element beyond the 5th year that could exist but doesn't because of the maturation in the 5-year annuity, okay? So, right? That's what's not received. So therefore, we'll write the present value of a 5-year annuity. So the present value of the 5-year annuity is the present value of whatever might be a perpetuity minus the part of the perpetuity that would not be received, right? So let's just kind of move along to the present value. So here's the perpetuity, and here's the part not received. So it's C over R times, right, 1 over 1 plus R, in this case to the 5th, because we're receiving, right, 5 years worth of annuity payments. Now you can factor out the C from both terms, right? You have a, see this common factor that sits, so you have a C here and here. So we could factor that out, okay? And what you could do with this is just rewrite it this way. So it would be like C times this, 1 over R. So this is this first element, right, is 1 over R. Okay, and then here it is again, right here. See that? So it's 1 over R minus 1 over R. Okay, and inside here we got 1 over, like, 1 plus R to the 5th, right? So you have basically, you have C times an annuity factor, we'll call this. So inside these brackets, right, inside the brackets is what's called the annuity factor. Okay, so that means generally we can rewrite the above. So do the general version. The general example of this would be present value of a cash flow. So that'd be C over R, right, times 1 minus 1 over 1 plus R raised to the T. So T is basically now, right, T is the length of the annuity. All right, so this equation, right, is a little bit different from Ross and Westfield-Jaffe. You can look closely at them. Okay, they're equivalent. This way of writing the formula, it's a little bit easier to remember. And right, so this formula, it's a little easier. I like it. Some people will want to use basically the textbook formula. That's fine. The key is remembering how you got to this point when we figured out, right, this is the present value of an annuity in its general form, right? So you won't fail at all if you understand how we got there. Let's do an example. Okay, so let's do this. We're going to take that. We want to know, we'll say, what is the present value? What is the present value of, let's do an 8-year annuity. Let's say that it's $150 per year. It's received at the end of each year. So this is a regular annuity. Let's say we'll say the interest rate R is 12%. Okay. So we just use this equation. We can say present value is, let's see, C is 150, okay, over R, 0.12. And then that's times 1 minus 1. And that 1 there is divided by 1.12. That's raised to the 8th power. And you can construct this carefully. Watch when you're in the spreadsheet, right? you make sure that you watch the formula that you create, so that you maintain these proper open and close parentheses, right? The brackets don't work inside the Excel formulas that you might be creating, okay? And of course, you can, inside Excel, also look up the regular annuity formula, which is just one of the functions embedded inside Excel, right? So if you run this through your calculator, you get 745, right? 745 and 15 cents, okay? Also in Ross Westfield Jaffe, there's a table in Appendix 2 that gives the present value of $1 received at different times and different interest rates. And in the above problem, you could look up the 8 years and the interest rate of 0.12, and you get a table factor. Okay, so the table factor in Appendix 2 is 4.9676, and you could take 150 times this factor, right? So this factor right here is what sits inside this parentheses, right? And it also, by the way, includes this divisor right here. See, so you could take the 150 times the 4.976. Oopsie. Oh. Sorry. 4.96. 4.9676. Okay. And you actually get there 745.14. So you have a 1 penny rounding error based upon our table. So what's going on here, right? You could make a deposit of $745.15. And you could, if you had that deposit going for, remember our interest rate was 12%, right? That you could draw from this deposit, right? 150 per year for each of the 8 years. And once you did that, you would have a zero balance in your account. You should check that and see if you can calculate that. Next thing we'll do, right? Let's look at an annuity due. Got to nudge that a tiny bit, right? The annuity due situation has the cash flows received at the start of each period instead of the end. So suppose that you had, let's do the example. It's a good way to kind of walk into this special case, okay? So you say basically, when you say this, what is the present value of an annuity due? Right. See it for $200. Let's say for 5 years, and R equals, let's say 9%. So the present value is, well, you receive the money right away in the first year, right? So that's $200. Plus it's the present value of basically, right, 4 annual regular annuity payments. Right? See, if you receive the money at the beginning of a year, you could calculate the $200 received in that first year, and then let a year go by, right? and at the beginning of year 2, that's the same number as the end of year 1 for the next $200. So this one actually winds up being present value of 200, right? And check this one too with the calculator or spreadsheet. Plus 647.94. Okay, so that's 847.94, 847. And what about a certain situation we'll call a displaced annuity? So this is an annuity that begins with a delay. Let's say really what's going on as our example this time, let's say you get $100 per year. And let's say that you're expecting this to go from the end of time period T4 through, let's do T through T equals 7, right? So you have, let's say, an interest rate of 8%. So the present value now here from our earlier formula is a sum of years that are now running year 4, 5, 6, and 7. So we're summing 4, 5, 6, and 7. It's $100. Over 1 plus r to the t, where, right, your discount factor now has to be in for the 4th year, the 5th year, the 6th year, the 7th year, right? Turns out there's 3 ways to solve this. Way number 1, you could bring back each of the years individually. See, so we're dealing with the span of time that sits between, right, for year 4 through 7. So you bring back those years. So the present value of the $100 per year runs like this. Actually, it's $73.50 in year 4, $68.06 in year 5, and it's $63.02 after that, and $58.35. Just got this off my spreadsheet. So you get $262.93 for the present value. Now that's okay, but it takes a lot of work, right? So the second method is to find the present value of a 7-year annuity and subtract the present value, right, of a 3-year annuity. So you do the full 7 years and subtract the present value of a 3-year annuity. So now the timeline is like, okay, 0. So these time periods, I'm going to do the full 7-year annuity, and then we'll also calculate a 3-year annuity and see what that does. It leaves you with this distance here, this distance which is equivalent to the present value from years 4 through 7, right? And so yeah, this is this piece here, right? This piece here was not received. That's why we're doing this little subtraction, right? So this actually winds up being, okay, 520.64 minus 257.71. That equals 262.93. All right, so the third way is to find out at the end of the year t equal 3, we could find the present value of a 4-year annuity and bring it back to the time period 0. Right, so imagine that you're at the end of t equal 3, and you want to find the present value of a 4-year annuity. So you could just do a 4-year annuity and utilize a discount factor. See, so it winds up being 331.21. So this is the year 3 value of this 4-year annuity. That's the brown element here, right? So what I'm doing here is going to 4, 5, 6, 7. Here's 3, right? So I'm taking those cash flows and bringing them back to year 3. Then you take the present value of what is the present value of year 3 stuff in year 3, turn it back into present value now, right? So you got to go, well, that's divided by our discount rate, our interest rate here is 8%, right? And that equals 262.93. No shocker there. See, $331.21, $331.21. That's the present value of a 4-year annuity at the end of the year t equal 3. Okay. So the next term, this discount factor that we have, brings it all back to time period t equals 0. Okay. And fourthly, we'll do growing perpetuities. My computer is not supposed to be doing that. I'm going to show you that page again. I think it might have blacked out. That's upsetting. I've turned that screensaver off, and so somehow it Apple does a funny thing, I guess, when I plug in all this technology. So what we're going to do is a growing perpetuity. You can pause that last slide there if you want to work through the text a little bit and double check the calculations. So let's recall, right? Recall that a perpetuity has a present value equal to the cash flow over the discount rate. But what if the cash flows are growing at a constant rate g? G will be our growth rate. So let's see, at C years, let's say C1 is what we get at the first year. And then the second year, it looks like this, C1 times 1 plus the growth rate to the first. And then another year goes by, so at the end of the third year, you have this cash flow that looked like what it did in the first year, but it had 2 years of growth for it, right? So be 1 plus 2 raised to the, or 1 plus g raised to the 2, and you can continue this, right? This growth is going on requires that you that you make accounting of this. You could continue this process all the way to the end, of course, right? You could go to C1, and it grew by 1 plus g to the n minus 1, we'll call it. And now suppose I wanted to have a discount rate on these, right? So in the first period, right, I would have discounted it by saying, well, let's go 1 plus r, right, to the first. In the second period, we would have gone a 1 plus r to the second, and so on, all the way through the last possible period. This would be at 1 plus r to the n. Now, if you multiply that equation, if you multiply this equation by 1 plus r over 1 plus g, and subtract this this particular equation from the resulting multiplied equation, you actually let n approach infinity. This is the same approach we used before with the perpetuity. Okay? And what you'll get is the perpetuity formula, which is the present value is the cash flow, okay, over R and minus G. So this is the formula that we need to know, okay, for a growing perpetuity. C1 is it's the first cash flow received at the end of the first year. So the idea is if you put the present value in the bank right now and you wanted to fund an infinite stream of growing payments, you want to know how big the present value has to be, right? And the interest generated on the investment is present value times R. So you want the the principal to grow at rate G to ensure that the payments can grow, right? So so that's what's going on. The interest generated the first year has to really subtract the present value times G, okay, and then pay out that amount. Now, if you want to do that, the principal that could be carried forward at the present value times 1 plus G, and you do it over and over again through the years. And what's going on, right? The present value times R, right, minus the present value that grew is equal to the first year cash flow. And that basically gives you the initial balance that you need to have in place to generate a payment stream that grows at rate G. Now, use of the equation requires some items of note. So first and second. First off, right, the rate of interest, right, has to be greater than the rate of growth. And then secondly, C1, right, the first cash flow, it grows at rate G forever. It grows at rate G forever. Let's do an example. So you expect, let's say, a $3 dividend at the end of this year. And you think that the dividend, let's say, is going to grow 6% forever. All right, so growth rate 6%. Let's say the discount rate is 15%. So how much would you pay for a share of common stock with such characteristics? All right, the present value of the common stock. All right, how much would you pay for? Just do 1 share. Okay, so present value is right, the first year cash flow over R minus G. You got $3, and that's over 15% rate for R, 6% for your growth rate. And you can double check this with the calculator, right? This runs $33.33. You just did something which we call valuing a financial security, right? Valuing a financial security. Now, I actually led you astray somewhat, so I apologize. There's another brief section or 2 or 3 we have to work on. So what I'm going to do is actually do a third section for the 4th series of videos. For now, we will stop recording and get this up on YouTube.